2 of our discussion of wastewater applications in terms of wastewater surveillance. So last week was a really broad overview of how we can use this tool. I'm really pleased to have Adelaide Roger this week to talk about more in-depth use of genomic surveillance in wastewater. So let me give you a little bit of background on our speaker. Adelaide is a scientist at Wisconsin State Laboratory of Hygiene. She earned her PhD in environmental microbiology from the University of Paris, France. She moved to Wisconsin to study bacterial communities in the environment and wastewater using sequencing tools. When the COVID-19 pandemic started, she pivoted to tracking SARS-CoV-2 in wastewater. In 2021, she joined the Wisconsin State Laboratory, where she monitors additional pathogens throughout the state. So please welcome Adelaide, and feel free to start. Thank you.
Thank you very much. Everybody can hear me just fine? Awesome. So as Erin just introduced, my name is Adelaide Roger, and throughout the presentation, if you have any question or if things are unclear, feel free to step in and ask your question. So yes, last week we had a really amazing presentation by Erin introducing what wastewater surveillance is, but just to recap in case to refresh everybody's memories. So the way it works is that when people are infected by viruses or bacteria, they, if they live in a city or in a place that is that has a sewer network, then all the bacteria or the viruses can be shed through the toilets, or if people take a shower, if they have blister on their skin, or if they brush their teeth. All these entryways can end up in the sewer system. The material, the genomic material, will convey in the sewer system to arrive at the wastewater treatment plant. For the big wastewater treatment plant, the operator are able to collect before the wastewater treatment plant, and that is really key here. So before any treatment is applied to the wastewater, they collect some sample that they send to the laboratory, who is going to perform the different analysis, either quantification or sequencing, and this information will be sent to the state or local health department, where epidemiologists can take action based on the level of certain disease in the community. The advantages of wastewater surveillance. So the first one, if we look at the wastewater level, is that it's a community level based surveillance. And so one sample is represent the entire community that is on that sewer shed. And that composite sample is completely anonymous. So we cannot opt out of it, and we are not providing any information about ourselves when we do that type of analysis. There is no geographic or demographic testing bias. And what I mean by that is that no matter what, we are living in a wealthy neighborhood or a poor neighborhood or a large city or a small city, at the moment we are part of the program, we are just represented the same way. And which allow us especially to have a better access to health outcome for the vulnerable population, including low income and uninsured people, as well as some minorities. And it's particularly important because these groups are high risk of poor health outcome. It's non-invasive, as I mentioned, we cannot opt out. And it's not based on test-seeking behavior. And so, as Erin mentioned last week, is the symptomatic as well as the asymptomatic, so people who are infected but present no signs of infection are tested the same way. It's relatively time efficient. There is usually about 48 hours between the sample is start to be collected at the moment we send the data to the authorities. And it's relatively low cost, considering that one sample can represent a million of people. It would, of course, not be the same price if we had to target, for example, for biggest city here in Milwaukee, that is 500,000 people, it would cost a lot to test this 500,000 people. So I wanted to talk a little bit of the National Wastewater Surveillance System. So it's a program that was developed by the CDC back in 2020 at the beginning of the pandemic. So before that, they had no national wastewater surveillance system. So it's really impressive how just in a few years, so now it's been 5 years, that there is about now about 1,400 sites across the entire nation that are participating in this program. Most of the data collected and generated by local laboratories as well as state laboratories. But you may have heard also of the national contract, which currently is Verily. And there is a map here indicating all the sites they are actually testing. And so Verily provide the advantage to release all the targets they are monitoring almost in their real time on their online dashboard. So you may have somewhere a site on your jurisdiction that is participating in the program. And the data are also collected and gathered by their academic partner called Wastewater Scan, which are closely working with Verily. So Erin mentioned last week that the SARS-CoV-2 surveillance, sorry, I tried to move that bar here. I don't know, nobody can see beside of me. Sorry, I lost track by doing that. In wastewater, when we do the regular quantification surveillance, we have information about the prevalence of a disease across time. So here you have the statewide average of SARS-CoV-2 in wastewater, expressed by gene copies per person and per day in Wisconsin. So here in January 2022 was the Omicron wave, and then you had different waves across time. It does not inform how many people are sick, but it does not inform about an important information, which is which variant are actually circulating. And what having information about the different variants circulating is important is that I took a screenshot of the World Health Organization website that indicate that some changes may affect the virus's properties, such as how easily it spreads, the associated disease severity, or the performance of vaccine, therapeutic medicine, diagnostic tools, and other public health and social measures. So reason why not only having the information about the quantity in wastewater is important, but also having which variant is actually circulating. And so you may have heard about all these really not that much easy to remember XFG, NB 1.8.1, or GN1, or XBB, or all these trivial names. They are categorized here within different groups. And I know there is a lot of text here, but the idea is just, I will share the slide and you will be able to read that later if you want to. But these different variants can be classified if they have of concern, so which is called VOC for variant of concern, if their variants has an increased transmissibility, virulence, and or decreased diagnostic, therapeutic, and vaccine efficiency. For the variants that are also of interest but not classified as of concern, they are classified as VOI, or variant under monitoring, and of course the ones that are no longer variant of concern. So on that website, outbreak.info, you have like that the classification of the different variants, the main group. So for example, XFG right now is classified as VUM by the WHO since June 25th, 2025. And it could escalate more if more evidence of issues that virus are reported. So some principle of how the SARS-CoV-2 variant surveillance works. So bear with me, I try to make it as easy to understand, but I wanted to introduce some concepts that maybe sometimes are hard to apprehend and help in the long run to better understand how all this surveillance works. So here you have the entire genome of SARS-CoV-2 and every section code for a different gene that will help either to create the envelope or replicate or infect the host, etc., etc. For a given, every single variant has kind of an ID of all the different mutations here that are symbolized on the top by this little dots or triangle, indicating that specific position here, for example, you had a mutation, and same here and more here. And when we look at delta, for example, you can see now how it's easy to distinguish a variant between alpha and delta because they don't have the same lot of mutation. With Omicron, it's getting a little bit harder because as you can see, there's more and more mutation. And so it's possible that one mutation can be shared between different variants. So it's getting more and more tricky to be able to identify and recognize the different variants. And to measure or identify these different variants in wastewater, there is two main approaches that are used, that I'm aware of at least. There is the quantitative PCR assays that are going to target just one unique mutation. It has the advantage to be quantitative, and he give information about the concentration of the mutation as well as the concentration of the non-mutation, which gives some ratio. It's really sensitive, it's highly specific, and it's super cheap. The limitation, it can only screen one mutation at a time, and it's not a proactive screening in the way that if right now, if tomorrow there is a new variant, the time we develop the PCR assay, the variant may be already gone. And especially with Omicron, you have so many variants that are sharing the same mutation, it can become pretty tricky. But there is I found some dashboard doing that. So in that case, it's the wastewater scan dashboard. You have in orange here, so I hope it's not too small, but you have in orange the SARS-CoV-2 in general concentration in wastewater. And the different here colors indicate if it's Omicron BA4 or the darker blue is Delta. And you can see over time that they were able to track the different variants based on that method. They stopped, unfortunately, for that specific dashboard in 2023. The other dashboard also I found is it was a project that is called Rosalind, in which they look at different mutation to be able to track different variants in the state. So it worked pretty well. So that technique works, but has some, I mentioned, limitation. The most common one is to do targeted sequencing. And by doing that, it's not looking at just one mutation, it's looking at different portion of the gene, of the genome, and that's allowed to have a broader coverage. The advantage is that it can screen multiple mutations at the same time. It's more proactive. It allows to have good trends over time, but the limitation is that it's semi-quantitative. I think the best way of looking at the data is using relative proportion. It's not as sensitive as PCR assays, good PCR assays. It's more expensive than PCR assays. And the turnover time can be longer. And here is an example of the CDC dashboard showing the nationwide trend of the different variants across time. So right now, the most predominant variant is XFG, and that's the one here that is in the dark blue. So let's look again at our SARS-CoV-2 genome. There is different ways of doing the variant sequencing surveillance. Is that we can only look at the specific small region. In that case, it's receptor binding domain. This is what is done by the state of Missouri. So they only sequence that. And the S gene is the gene that allows the host, the virus to bind to the host. And for that reason, to evade as much as possible the immune system of the host. That small region here, it has to mutate quite a lot. Otherwise, they would just wouldn't be able to escape the immune system. But there is also the other method that is used is to do the whole genome sequencing. And the way it works is that you may have heard about tile amplicon sequencing, which is small fraction of the entire genome are going to be sequenced, and overall you will have the entire genome sequence. And I just mentioned that here in case you've heard about it. There is two main sequencing technologies that are used to do whole genome sequencing. which is Illumina that generates short reads. So will need to have more portion of your genome sequence. Or you also have Nanopore, which can generate longer reads. So depending of which one, you can even for the Nanopore just have a few magnifier to be able to cover the entire genome. Sorry, I keep saying gene for genome. So the big principle, you have an unknown strain, you sequence it, so you have your little fraction here that I was symbolized before by a magnifier, and then you sequence them. And once you sequence them using a bioinformatic pipeline, you can align them on your reference and be able to then see like, oh, here it's actually different from the reference, so this is actual mutation. And using data analysis and visualization, you're able to say like, oh, I recognize that pattern, it's alpha, or I recognize that pattern, it's delta variant. The challenges associated with that is the fact that you may have heard about this terminology when you look at some webinar. So again, here's the SARS-CoV-2 genome, the entire genome. And in that specific example, we will say with by looking at 9 fraction of the genome, 9 fraction of 9 portion of the genome, you have 100% of the genome coverage. And the depth is the number of reads that you have for every single location of your genome. Why both are important is that if we only were sequencing here, we don't have the same information that if we have the entire genome. And the depth, of course, we have more confidence in the data if we have 1,000 reads as if we only have 1. And that is the fairy tale. We want a lot of depth. We want a big depth and 100% of the coverage. The fairy tale, the reality of the fairy tale is not as good. You can have issue with the coverage and the depth. So for example, in that context here, that area is not as well sequenced as the depth is not as deep as the other one, but it's still okay to pass the QC. While this one, obviously, there is so poor coverage everywhere. It's even hard to be able to say like, oh, for sure, that variant is delta because I can find that mutation and that mutation, because there is too many gaps to confidently be able to call some mutation. This issue with the coverage and the depth, and that is really important, can be enhanced by sample processing. And the sample processing being the concentration of viruses, of the pathogen in general, and the extraction. If the sample processing degraded the nucleic acid, then if here, for example, it's in that specific region here, the genome have been degraded, so trimmed, then we won't have that coverage at all. So that's really can be an issue. And if the recovery is really low, because the sample processing is not great for that given sample, then it's going to be really hard to have good quality data because what you start with is so little, but at the end you don't get that much. So that's not that's a big problem to consider. There is also inhibitors, and in wastewater is just full of inhibitors. One of the big challenges we have here in Wisconsin is the industrial discharge that can really reduce the PCR efficiency. And there is some areas that we know are easier to sequence than others. So if there is any inhibition, then we will have gaps in these specific areas. And if it's the gaps, as I was showing before, where we have a lot of mutation, then it's going to be really hard to be like, oh, for sure we can find that variant in the sample. We have some sequencing errors, which are relatively easy to identify, except if the coverage is really low. Like for example, in that case, the red little radioactive sign are actual mutation, but the black one is a sequencing error. If we have a lot of reads, we're able to say like, no, for sure, this one is not legit. But if we have just a little amount of depth in a specific location, it's really hard to be like, oh, it's a sequencing error or an actual legit mutation. And of course, in wastewater, we have multiple variants per sample. And so here to summarize here the clinical that I work only on the environment, and I kind of dream when I think about clinical surveillance in the way that in one sample, you will have one or just a few variants, and most of the sample will be what you're looking for. while in wastewater, most of the thing you're looking for are actually really low abundance, because most of the other things are not the thing you don't want to look at. And it's almost impossible that they're going to have only one variant circulating. It's going to be 1,000 if you're lucky, but maybe 1,000 of different type of variants. 1,000 is maybe a lot, but at least hundreds. Once you have this information, you have some strong bioinformatic tools that are going to look at the mutation frequency. In that case, you have 100% of mutation frequency, or only here 60. And with the depth, you are able to process this information into every sample has that much of 10% of that variant, 80% of that variant, et cetera, et cetera. The big one I could think of when I did the presentation are VPipe, but you may have heard about FRIAD, which is widely used, and it's what we are using here in Wisconsin for our dashboard. And the plot underneath is a screenshot of our dashboard. So despite everything I just mentioned, it looks like it's never going to work, and that's initially what I thought it would happen. That's never we would get good data out of wastewater. As you can see here on these two plots, so the left one showing the relative abundance of different lineages within the clinical data set that I was able to gather from covariant.org. And when you compare them with the actual relative abundance we found in wastewater, it's actually matching super well. And that was really like, wow, that's what we are doing actually works. And when we started it back in 2022, I had no idea that would work that well. And above everything is that now that the number of samples that are tested in the clinical surveillance are decreasing. As you can see here, before they were sequencing up to like 10,000 samples every other week. Now they are arrive almost to like just a dozen of samples every other week. And so, as you can see here on the clinical trend, when focusing only to the Omicron KP3, like the trend is actually more robust when you look at the wastewater signal than when you look at the clinical signal. And it's just based on the fact that when I did that presentation, so back in 2024, it's not the most recent slide I made, but in August, they only had 6 samples that were sequenced on the clinical side and only 3 in September. While on our side, we had about, I would say, 50 samples that were sequenced on wastewater, which is not that many, but it's also important to consider that one wastewater sample, it's depending on which site we are looking in Wisconsin, it's between 2,000 people up to 500,000 people. So that's one sample is already many people. So that's the reason why we are thinking that our trend looks really good and are really robust compared to the clinical trends. And here it's exactly the same plot that I showed previously. So the y-axis is the proportion between 0 and 100. But this time I split them per different variants. And as the blue bars represent the clinical signal, while the red bar represent the wastewater signal. And as you can see, for all the different variants that I was, when I did that presentation, you can see that both the clinical and the wastewater signal rise and decrease about the same times. And it was also interesting to see, for example, we were able to detect some delta signal back in early 2022, which was absolutely not found in the clinical surveillance. And some that signal was validated and confirmed by a digital droplet PCR. So really to indicate the good correlation between the clinical and the wastewater variant proportion, with some that goes up almost to 0.99 R-squared. So the targeted sequencing for at least SARS-CoV-2, it's semi-quantitative, it's relatively sensitive, and it allows to, at least at the Wisconsin level, to have spatial and temporal trends. And it gives information of the predominant variants that are circulating. And here are some dashboards that I picked that are near your areas. So there is Missouri is maybe a little bit further, but that's I wanted to put it here in because it's they're able to track the variant by only targeting the beginning of the spike gene. So I think it's really valuable and really good to see that they are able to track even now all the different variants circulating. I repeated here the CDC National Wastewater Surveillance System dashboard that I presented previously. There is also the Texas Epidemiologic Public Health Institute that has its own dashboard showing the different SARS-CoV-2 lineages over time. And so you can see like that when some lineages are rising and when they disappear. And here are some dashboard from the wastewater scan when they do sequencing. So you can, as I mentioned, as I show for the state, for our state, you can see based on the bars, which variant is the most prevalent. So right now in orange is XLG. There is SARS-CoV-2 is not the only pathogen we can actually sequence, and the second one we were considering here in Wisconsin is influenza A. We had some issues initially doing influenza A, and we still have issues doing influenza A because we were thinking, oh, if now we manage to adjust our, sorry, I hope you cannot hear that. If we're successful to do sequencing out of, if we're able to do SARS-CoV-2 sequencing out of wastewater, we are going to do well doing influenza A sequencing. So just for recap, influenza A is not like a long genome as SARS-CoV-2. It's composed of 8 segments, and every single of these segments code for a different gene. And so initially we were like, oh, we're just going to use the clinical primers and do influenza A sequencing. That's going to work great. And the way these universal primers works is that for every single of the 8 segments, they amplify using primers located at the beginning of the segment and located at the end of the segment. And so this is what they do. And then after they do the sequencing out of it, and turns out in wastewater, it did not work. And we were not the only one finding that. While Missouri, who was able to do like just one region of the HA, was successful. So we were like, okay, maybe the issue we are facing is the fact that in wastewater, either the influenza A segments are degraded inside the sewer, or our method is too rough and degrade the different segments, and so we cannot have the whole segment sequence because somehow some of them are just trimmed in the middle, and so for that reason, because they are trimmed, you cannot sequence the entire segment. So the way the community is switching, the wastewater community is switching is to do tile amplicon sequencing, as I previously described for SARS-CoV-2. And they are targeting 2 main genes, which is the HA gene, that's coding for the hemagglutinin, as well as the ANA gene, which is coding for neuraminidase, which is coding for the neuraminidase. Why these 2 genes? Is that because it's these 2 that are used to call a different, to do subtyping, and the subtyping, the H1N1 come from HA, that as type 1 or NA1. So I said that because I was surprised when I discovered that, because I'm not a virologist. And of course, some are able to do the whole genome sequencing, but a lot of effort in the community is based on just looking for these 2 specific genes. And I put here a screenshot of a preprint, so not peer-reviewed yet. That's a study that was done in Switzerland, and where they were able to look at H1N1 clade. So they are really they are able to, even more than subtyping, to clade train over time. And in that study, they were able to do that train, that time train by looking at the HA, I forgot to change here, NA and the M genes. And I really allow them to do some spatial and trend monitoring, see which clade is the most predominant. And what I put here with confirmed clinical trends is in the fact that there is some people in the community that says that wastewater would help designing the next year's vaccine. And I think this is true in the way that it's not necessarily looking at the actual genome, the actual sequence by itself that would help, but it will help knowing if the clinical clades if the different clade they found in a clinical surveillance match the predominant clade that are also circulating in the population. Let's say, for example, the clinical surveillance only picked up on the dark blue here, while the wastewater is also able to pick it up, but the wastewater will be able to say like there is also that light blue that is circulating that was not that well represented in the clinical data, but maybe would be interested to also taking that into account to develop next year's vaccine. Targeted sequencing also allows to confirm PCR assay results. And a recent example is for us measles. So I put some example here of a typical dPCR assays. So you have the positive signal on the top and the negative signal on the bottom. When you have a lot of a positive signal, it's pretty unambiguous that that sample is positive. That's not measles here, don't worry. It's just an example, but if we had that, it's unambiguous. For sure, we have in that context measles in the sample. But if we have this kind of results, it's pretty hard to say, is it a false positive or is it actually detected? And one of the ways to actually validate if these signals are legit or just false positive is to try to sequence them. And our partner in Colorado was able, not for us, but for another lab who only had one positive partition, to be able to sequence the measles genome. And that's a no-brainer. If you can sequence the genome of a given pathogen in your sample, then for sure it's in there. So that's really a strong validation for the public health to be able to say to them like, hey, we actually detected it and we can actually find the genetic materials. So this is not a false positive, this is actual real positive. And after the public health can actually take action to remediate or constrain the outbreak. Sequencing can also allow to distinguish between wild type and vaccine, and that's the case for measles as well as for polio. Because the assay, for example, for polio does not, the assay that is used to quantify polio does not distinguish between the variants, the wild type, and the actual vaccine. So sequencing is the only way to be able to say like, for sure what you have is actually a vaccine and not the actual wild type version of polio, which is obviously not the same response for the local public health department. And the wastewater can also help linking the wastewater and the clinical specimen. And what I mean by that is that recently we were doing the NFL draft monitoring in Wisconsin in the Green Bay area. And we had, which was not expected, of course, a pretty strong hepatitis A signal in our sample. With that, that was not as high as the sample that is here, but was pretty high to be able to say like, this is not a false positive, this is real. And they were able to locate the actual case. So just to give more context, hepatitis A can take from 14 days to actually have the first symptoms to 50 days. So that can be a really long time before the first symptoms are shown. And so for the first person to be found in the population. But during that time, they can be contagious. So the thing can not go wild, but it's good to take measure as soon as possible. And so when we detected it, we didn't know if it was somebody who got infected by somebody who came to the Green Bay area for the NFL draft, or if it's somebody who was infected naturally in the area, and if the signal would just disappear after the NFL draft. Turns out the signal did not disappear after the NFL draft. So if the contamination occurred because of the NFL draft, the signal was still in there. And we were able to locate about a month and a half, 2 months later, an actual clinical case. We were able to sequence the hepatitis A genome. I won't say we, Colorado, our partner in Colorado, were able to sequence the genome, the hepatitis A genome. And we are still waiting for the clinical case to be sequenced by the CDC to be able to confirm that it's actually the same case. And if it's not the same case, then that means somebody else is sick in the area, and the local public health should still looking for that person to contain the outbreak. So after last week, Erin talked about targeted sequencing, but she also mentioned about metagenomics. And so just to distinguish the two, the targeted sequencing, and there's huge typo here, is to look really on specific organism. In that case, it looks like viruses, and there are 3 of them. So the targeted sequencing will only look for these for the same viruses, and it can even be like a tiny portion of the genome within these viruses. While the metagenomic, or if you've heard about shotgun, is going to sequence everything that is in your sample. And so that can be tricky for surveillance, especially if you are looking for, just like in the case that I highlighted it here, that diplococci, that's the only one that is on that visual. So that means if you do metagenomic and you want to have access to that information, to the genomic material of that little organism here, you will have to sequence really deep, because most likely each time you pick up, as you sequence something in your sample that's going to be the abundant organism, and it can happen that right away you will pick a rare one, but most likely you will get the abundant first. But there is some research, and I think right now it's mostly research application of metagenomic for wastewater surveillance, but most likely soon enough, it will be a regular tools, because you would have told me like in January 2020, if I would be able to do SARS-CoV-2 sequencing in wastewater, I would have said like, hell no, that's never going to happen. That's impossible. And same for influenza. And then here we are. So it's most likely the future of the surveillance. And the advantage of metagenomic is the fact that it's full agnostic screening, since you're sequencing everything in your sample. And so it's not just like, oh, so because it's agnostic, if, for example, tomorrow we have SARS-CoV-3 that's coming in the population, then we don't need to have already the primers developed to sequence SARS-CoV-3. That type of method will allow to detect it. It gives information about the absence presence. I agree with Erin what she said last week, which is does not provide trends, even if what I'm going to show you on the right kind of show that we can see trend, but maybe the better word would be we can see patterns, and we can see what is predominant and what is not. And in that project, so the dashboard is available here if you are interested. There is a few cities across the nation that are participating in that project, where they are doing deep sequencing, and it's billions of reads per sample. So it's where it's quite pricey, but maybe it's not as pricey considering the information we can get out of it. And in that case here, summarized for Columbia and Missouri, the abundance of different respiratory viruses. So the scale, just to contextualize the information, so you have a scale, so let me rephrase. On the y-axis, you have different pathogen. So pneumovirus RSV-B, you have RSV-A, influenza C, B, you have some influenza A across time. So in that case, January 2024 to August 2025. And the intensity of the blue color indicates the number of reads. And I didn't realize I was covering the thing. It's reads per billion, number of reads per billion reads. And it's a log 10 scale, which indicates that 0.5 means that they found 3 reads of that specific virus within billions of reads per billion. So they shouldn't have S here, but anyway. And while here, the darker color indicate that they had about 3K reads per billion of reads. So that's pretty low, but still, it's still variable. And thing that I was interested to see is that you see the influenza outbreak mostly during the winter. So you can see it's influenza, then during the summer you don't detect it again, and then you start detecting again during the winter. So I think it's pretty variable. The issue I can see talking with our Wisconsin Department of Health Services that if you start finding something that you have no action plan, what do you do with that information? Like, for example, if they start seeing polio, what is the response? There is no response. There's no clear plan established at our Department of Health Services. There's also information about enteric viruses because enteric viruses are easier or spread better through feces. You can see that the log is higher. You have millions of reads per billion reads. And they also have animal viruses. And I'm guessing that was to also show some information about H5. But anyway, the thing I thought was interesting while hanging on their dashboard is, for example, if we compare Columbia and Missouri, which I would say is quite rural, compared to Chicago and Illinois, it was interesting to see that all the signal associated with pig is not as strong in Illinois, which I would assume there is not that many pig farm in the middle of Chicago. While it was interesting to see that it sounds like there is way much more rats in Chicago than in Missouri. So I thought it was interesting. So we can see trends and patterns and things like that looking at their metagenomics. So for that, I think it's pretty cool. Another way also it's used extensively is to do some antimicrobial resistance monitoring. And that is the case here for a study I found where they look at different antimicrobial classes as well as some specific genes. So that's also used quite extensively in that domain. So I may have said a lot, hopefully not too much, but if you need to not watch my presentation again, but if you have like a take-home message, I really strongly encourage looking at that 4 minutes video of the CDC. It's on YouTube and it's super well explained. It's not going to go as much in detail as I did, but it's actually really well explained. So if you have one take-home message, look at that video and then yeah, that's really the take-home message of my presentation. And I did not mention it previously, but all the news sites, so the National Wastewater Surveillance System, there is 6 COEs, so Center of Excellence. In Wisconsin, we are one of them. But if I put that map, it's because you may have in your area either North Carolina, and I couldn't find any contact. But if you are in that area, you should reach out to Houston if you have questions about some assays or how to implement some methodologies and things like that. The thing that is unique with Wisconsin, we are regularly doing a proficiency testing where we are sending the same sample over the state. So if you would like your site, your lab to be enrolled in the program, let them know or let us know and we can reach out to them. It's completely free. And the next one that will occur, I don't know when, but hopefully before the end of the year. So yeah, if you have any question, don't hesitate to reach out to me or to reach out to one of the Center of Excellence in your jurisdiction. So on that, that's the end of my presentation. Thank you very much.